Okay, so in this video we're going to be talking about orbitals once again, and it's going to be kind of a part 2. There's also going to be a part 3 for an extended version of electron configuration. Now, as mentioned last episode, I mentioned that orbitals were areas in which scientists presumed that electrons had a high chance of being in. And I've mentioned that there are 4 main types of orbitals. First of all, S, P, D, and then F. And S had 1 space, as seen in this representation of a square. P has 3 spaces, D has 5 spaces, and F has 7 spaces. And the thing about orbitals is that they are a hard concept. It's a hard concept to grasp your mind around. So when I mention today in this video about these properties, these principles, don't think about them too hard. Don't try to understand them too deeply. Just try to understand them briefly, and then when you understand them briefly and generally what they're talking about, memorize them and just use them in problems. Don't wonder too much on why they are the way they are. Now, the reason that these spaces are important is because, first of all, we're going to have to look at Pauli's exclusion principle. Now, Pauli's exclusion principle states that for every single one of these squares, 2 electrons can fit in 1 square. And if we say this is kind of like the square that we see on top, Pauli, the scientist, states that electrons can either spin right or left. Now, don't think about why. Just try to memorize and understand afterwards. Now, let's say this is an electron. And Pauli states that in every space there are 2 electron vacancies. Alright, 2 electron spaces. Now, how we denote this is that if there is a square, if there is 1 electron in the orbital, we denote as such an arrow going upwards. If there are 2 electrons, we denote as such with 2 opposite facing parallel arrows. Now, there is no case where there are 2 arrows pointing upwards or 2 arrows pointing downwards. It's always 1 arrow pointing upwards and 1 arrow pointing downwards. So if we use the Pauli's exclusion principle on these 4 types of orbitals, you can see that for S there are 2 possible vacancies for electrons, so there are 2 max spaces for electrons to be fitted in. Now for P, since there are 3 boxes instead of 1, we can presume that there are not 2 but 6 spaces at max that electrons can fit into. Now for D, this will be the same. There will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And there will be 10 max spaces that electrons can fit in. The last would be 14, since there are 7 boxes and 7 times 2 is 14. So we've memorized that S, P, D, and F, these orbitals, have 1, 3, 5, 7 spaces each. So in order to get the max number of electrons these orbitals can fit in, we just need to multiply the designated spaces by 2 in order to get the max number of electrons. Now, taking a look at the second principle, Aufbau's principle. Aufbau's principle states that when electrons are first introduced to an atom, they aren't randomly just inputted into these orbitals. They actually have a very strict electron configuration. And last lecture, I've mentioned that in electron shells or orbits, there are these orbitals. In the first orbital, first orbits, there is the first orbital or subshell, 1s, then there is 2s, 2p, 3s, 3p, 3d, and 4f, and etc. But it is very difficult to memorize the levels of orbitals, or which orbitals are filled in first. So instead of just plainly memorizing, I will be explaining how to memorize using the periodic table very soon. But for now, just know that the first few are 1s2 and 2s2, 2p, 4, 6, and the list goes on. So what this basically means that 1s is the first s orbital, the first s orbital. What this means is that it's the second s orbital. Now, just because there is a 1 and a 2 here doesn't mean it has double the space. It just indicates what number of orbital they are. Now, this might be slightly confusing. The second p orbital is actually the first, but we denote it as a 2. And we are going to learn about that more in here. Now, for now, we just need to know that they fill up in this order, from the smallest to biggest. Now, taking a look at the next rule, Hund's rule, or often known as the bus rule. The bus rule. Bus rule states, or Hund's rule states that if there are, for example, a p orbital area, in which case there will be 3 boxes and 6 max electron spaces, it states that when electrons enter, let's say this is p, orbital p, they do not enter, the first one obviously enter in the first box, the second one does not enter right next to the first electron. It actually enters in the next box. And if a third electron is to come in, it would be placed where there are no electrons. So the Hund rule states that electrons try to figure out where there are blank spaces, and they prefer to go to these blank spaces instead of sitting next to or being next to a partner electron, like sitting on the bus. So if we know these three are the basics of how electron configuration is conducted. And the second part is by learning which orbitals are filled in first. And we call that electron configuration. And this is a simple way of figuring out how we write electron configurations for any atom in the periodic table. Now, in the periodic table is in almost any test, in AP, regular, or competition. The periodic table is almost always given to us, so we can use the periodic table to figure out the electron configurations. Now, these elements or atoms that are on the most right corner or right side of the periodic table, they are called noble gases. And this is very important to learn about electron configurations when we are going to be talking about condensed electron configurations, but just know for now that they are called noble gases because they have full electron shells. Now, how we view this is that, first of all, the first two are 1s and 1s because s have a max electron count of 2. Now, moving down to the second layer, we have 2s. Now, this 2 doesn't mean that it has double the space, it just indicates that it's the second s orbital. And once again, it has 2, so there are 1 and 2 spaces. Now, p on the other hand has 6 max electron spaces, so we have 1, 2, 3, 4, 5, 6. and 2 of s again. 1, 2, 3, 4, 5, 6. 2 again, and now there are these. Now these are introduced and they have 10 vacancy electrons spaces at max. So they occupy 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the list goes on simply all the way to the bottom, except that in these cases they are considered F. So just keep that in mind, although it almost never comes out in regular chemistry. Now we know that which orbitals are filled in first. Now we can try some real life examples. So let's try out hydrogen. So hydrogen is the first atom on the periodic table. So we can see that the electron configuration would be denoted with 1s. So we write 1s. Now, and since 1s has a space of 1, we write or draw 1 square. Now, since hydrogen at its neutral state has 1 electron, we draw 1 electron, and this would be denoted as 1s1. Now, taking a look at this writing, this would be 1s would be the writing of the electron configuration on the periodic table. Now, taking a look at the second notation, the second number up top, this would be the number of electrons that is in the current orbital. So since s can have a maximum of 2 electrons spaces, the highest number that will be written on top of an s will be 2. And for p, it would be 6, d would be 10, and f would be 14. So you would never see such notation, because for s there cannot be 5 vacant electron spaces. Now taking a look at the second example of helium. Helium is the second element, so it is still 1s due to the fact that helium would be right over here, and it still is denoted with 1s. But helium, on the other hand, has 2 electrons, so there will be 2 electrons instead of 1 in hydrogen. And since there is still only 1 box of 1s, this would be 1s, it would be drawn as such. Now lithium, on the other hand, goes down to the second period, where it is denoted with 2s. Lithium would be right over here. So it is denoted with, this is 1s and this is 2s. So basically it stacks up on top of each other. 1s would, since lithium has 3 electrons, how this would be filled out is that the first electron would go in 1s, and the second electron would not go in 1s as well. It would go in 2s due to the fact that Hund's rule applies. And then the third one would go in the 1s as well, because it goes in the lowest ranking orbitals first, due to the fact that Aufbau's principle applies. So lithium would be denoted as 1s2 because there are 2 electrons inside the first orbital of 1s, and there are 1 electron in the orbital 2s, as we can see in this graph or chart. Now for carbon, if we locate carbon in the periodic table, we can see that carbon is 1, 2, 3, 4, 5, 6. It would be here. This would be carbon. Now this would be on the category of 2p. So we not only write 2p down, we have to write 1s down, then 2s down, and then 2p. So this would be 1s, this would be 2s, and this would be 2p. Now since p has the max electron vacancy of 6 and it has 3 spaces, we write 3 boxes. Alright. Now, carbon at its neutral state has 6 electrons, so due to the fact that Hund's rule applies, 1s fills in, 2s fills in, then 2p fills in. Alright. Now, the first s is filled in, second s is filled in, and then finally the second box of 2p is filled in. So when we write this into notations, there will be 2 electrons in 2s, as we can see here. There will be once again 2 electrons in 2s, and there would be 2 electrons in 2p as well. So this would be how we denote this. But now, as you can see quickly, that although we have done examples that are upper on the periodic table, as we go down, it becomes difficult and more laborious to write electron configurations simply by hand. For example, Mg12 magnesium. It would be very, very uncomfortable because it has electron configuration of 12, and that would be very much more harder than such examples of carbon, lithium, and helium, which just have 2, 3, and 6 electrons. So how we do this is that I've mentioned before that noble gases are very important, and the reason noble gases are important because we can use them to write condensed electron configurations. We can use noble gases to write condensed electron configurations. These are the noble gases on the periodic table, and an example of this is how we use the condensed electron configuration is that if we have an atom here that we have to write the electron configuration for, we only need to write the noble gas that is smaller and nearest to the one that we need to solve. So this would be argon, I'm pretty sure. Or let's say that it is a noble gas of X. So how we would write this electron configuration is that we would write this mysterious noble gas in X in big parentheses, and then we will write 5s1. For example, if we have to get the electron configuration for this atom, we would see that the closest noble gas that is smaller is right over here. So let's say this is Y, and the condensed form would be Y. And since the one that we have to solve is in 7s after this condensed noble gas, we would write 7s1. That is how we write condensed electron configurations much more quicker for bigger atoms. Now the last thing to mention is paired electrons, and paired electron is just kind of a plus alpha. Doesn't really come out too often, but it's kind of this base knowledge that everyone needs to have. Basically, when there are 2 electrons in a single box, we call them paired electrons. And if they aren't paired, they are called unpaired electrons. Quite self-explanatory. And this is quite important in later chapters of chemistry as well, when we are going to talk about more complex things in chemistry.